We'll move on now from linear models to exponential models. An exponential model is simply trying to model our physical scenario as an exponential function. So we'll fit this to a real-world problem. We may multiply by a constant out front. We may write this as f of x equals some constant c times a to the x. So what is the interpretation here? Well, a is typically related to, do we double our amount, triple our amount over a given time, or etc. We might even have the quantity decay over time. That is, we might ask to write a model for a property that is getting smaller with time. A typical example of this for exponential models would be like radioactive decay, where you start with a certain amount of some substance, and after every fixed time interval, half of it has disappeared. This time interval is typically called a half-life. We'll look at a model where we have growth. So over a fixed amount of time, whatever I started with will grow by a certain factor. And the constant here corresponds to like our starting amount. And the intuition here is that if I plug in x equals 0, I have c times x times a to the 0. And no matter what a is, anything raised to the 0th power is always 1. So I'll just end up with c times 1 or c. So that's why the interpretation of c as the starting amount is very much dependent on having an exponential model. So the idea here is that we can solve problems with this sort of daunting looking model using our properties of logarithms and exponentials. So let's just recall how the logarithm can be used to solve exponential problems. It goes back to what is the definition of the logarithm. If y is equal to a raised to the x power, then x is equal to log base a of y. So this allows me a way to get access to what's happening in the exponent. And this type of relationship will be essential when we model exponential functions. So again, let's review some of these basic rules, which may be useful to us as we complete different problems. Excuse me. So of course, first we have that addition in the exponent becomes multiplication outside. We also have that if you have the same base but different bases but same exponent, instead of doing two separate exponentiations and then multiplying, I can first multiply and then exponentiate. Another important one, which we've seen used quite a bit, is this property of iterated exponents. So if I have a raised to the power x, and then I raise the output of that operation to the power y, this is equivalent to doing just one exponentiation, with exponentiation by x times y. So just as an example of that, if I wanted to compute 2 to the 2 to the 10, I could, of course, write this as 4 to the 10 by evaluating 2 squared on the inside, but this is also equal to 2 to the 20 by using the rule for iterated exponents. So you want to be comfortable making these types of relationships, especially as we start to work with exponential models, as it'll make the algebraic manipulations much more straightforward if you understand sort of the mathematical theory behind everything. And then something that's really essential to our models is the fact that anything raised to the 0th power is equal to 1. So the key point for exponential models in this question is that if I write f of x equals c times a to the x, which is the same model I illustrated right here, then f of 0 is equal to c times a to the 0. And a to the 0 is just 1. So I end up with c times 1, or just c. So this is really very important to understand. Exponential models say that at x value or time value 0, the only output of the function is that constant c. And then I allow the exponential rate to start taking over. So it's important to understand that interpretation. So let's review sort of the basic plots of exponential functions so you can understand what types of physical systems would benefit from an exponential model. So of course, the most salient property is that they have extreme growth. So here I have y equals 2 to the x. So here I have, I'll say, rapid growth as x gets bigger. And we can also see this just by writing out a table. So at x equals 0, I just have 1. At x equals 1, I have 2 to the 1, so 2. At x equals 2, I have 2 to the 2, so 4. At x equals 3, 8, 4, 16, 5, 32, and and so on. So it really grows very rapidly. In general, exponential functions grow more rapidly than any polynomial. I mean, this is one of the key properties that you show about exponential functions in calculus. It's really a very classic argument. So the idea is that if I can model something as an exponential function, it really should be growing very, very rapidly. Otherwise, the model is going to break down at a certain point. In many of the examples we'll look at, exponential models are used to describe things like populations of species. So perhaps the exponential model is valid up to a certain point. But of course, exponential growth cannot be sustained forever. After a certain point, the strain on resources becomes too great. And the population is essentially not able to grow anymore simply because there are not enough resources to go around. So these types of models have to be taken with a grain of salt. Very few things in the world really exhibit exponential growth indefinitely. Everything is eventually constrained. So it's important to keep in mind that the types of questions we're asked about is not really what research scientists do. Exponential models are sort of a first attempt at describing the situation. Refinements are made later. And in fact, there's a whole subject devoted to generalizing exponential models to, say, biological phenomenon. But this is something, if you're interested in, you can certainly send me an email about, and I will be happy to correspond with you. So let's look at a different model. This is the model for exponential decay. So the only thing I've changed here is the minus sign in the exponent. And now, instead of having growth, I have rapid decay to 0. So notice that instead of getting bigger, I'm getting very, very close to 0. But you might recall that I mentioned we have a horizontal asymptote here. So I never actually get to 0. But I do get very close. And I get very close very quickly. So what kinds of phenomena are typically modeled this way? Well, the real go-to example, in my opinion, is from physics and chemistry. It's radioactive decay. And the idea is that if I maybe start with 100 grams of some radioactive substance, after a fixed amount of time, I go down to 50, then 25, then 12.5, then 6.25, and so on. And all of these time intervals are the same, say 1 hour. So a key point is that the rate at which I'm decaying here is not constant, but the time interval in which it takes me to decay by a factor of 2 is constant. So after each fixed time interval, compared to the previous one, I'll have, say, half of what was left. or what I had before. Keep in mind that the 2 here is not necessary. We could use any kind of base. We could use 3, we could use 1/3. 2 is just a particularly convenient example, since generally it's easy to compute powers of 2. So let's look at an example. Suppose we have a population of javelinas, and they double in size every 16 months. That is, I start with a certain number of javelinas, and after 16 months, there are twice as many as I had at the start. Of course, again, this is not necessarily a reasonable model for the long term. Eventually, you're going to have way too many for the ecosystem to support. But this is just an example of mathematics in action. We would, in reality, refine this model more carefully. But for now, we'll assume it's accurate. Let's say that there are 100 to start. Part 1, I want to write a population function in terms of the number of months. So I want a function that will input the number of months and output how many javelinas I have at that time. How can I do this? Well, let's recall what the exponential model looks like. It would look like P for population at a given time, t, should be equal to C times, say, a to the t. It's a little hard to see that. So let's say times a to the t. So in this case, we have to determine Ca and any other relevant quantities. So how many do I start with here? Start with 100. And I mentioned that that constant out front is typically your starting amount. So in this case, C will be equal to 100. So this is part A. Now, I need to figure out what my base factor is. So am I talking about doubling, tripling, quadrupling? Well, I'm saying the population doubles after a given amount of time. So in this case, my constant A will just be 2. Again, coming from this doubling. But I do have to make one concession now, which is that I don't double every month. I double every 16 months. So instead of putting t here, I'm going to put t divided by 16. So when I put in t equals 16, I have 100 times 2, so 200. When I put in t equals 32, which means I've doubled twice, I should get 400. So let's check this a little bit. We'll do what I might call a sanity check to see if the function we've come up with is consistent with what we expect. So at t equals 0, I should have the original starting amount, 100. And I do, because I have 100 times 2 to the 0, which is 1, so just 100. How about after 16 months? I should have doubled by then. Well, P of 16 is 100 times 2 to the 16 over 16, so 100 times 2, so 200. So that makes sense. After 16 months, I've doubled. And then just for good measure, plugging in 32, I would expect to have 400 because another 16 months has elapsed. So I've gone from 100 at 0 to 200 at 16 to 400 at 32. And I get that because I have 100 times 2 to the 32 over 16, so 100 times 2 squared, so 400. So keep in mind that to answer the question for part A, we didn't need to make this table. It is, however, a nice sanity check to make sure that what we've come up with is consistent with what we're being asked to create. So let's look at part B now. It's asking me to find out how many javelinas I'll have after 6 years. So I think the first thing you might try is to plug in P of 6. But this is incorrect, and I'll give you a second to think about why. Well, we have to remember what type of input we're expecting here. Time is measured in months for us. So in order to plug 6 years into this problem, I need to first convert 6 years to months. So it's 6 times 12, so I guess that's 72 months. Okay? So that's what I'll plug into my formula, not 6. You have to make sure with your models that the inputs you put in are in the correct units. Otherwise, you can get very tricked up. And of course, the CLEP exam loves to do this. They love to give you a model in one type of unit and ask you a question in a different unit. So it really checks that you're paying attention, that you can first do the simple unit conversion and then use the model. So we checked P of 72, which is equal to 100 times 2 to the 72 divided by 16. Okay, so do we want to perhaps simplify this? Well, we can try. 100 times, let's see, 72 divided by 16 would be like maybe 9 over 2. Okay, so we could estimate this, right? 2 to the 4th is exactly 16. 2 to the 5th is 32. So we can do a little bit of estimation here. And I don't know, 2 to the 9 halves, maybe we'll say that's about halfway in between. So 24. So maybe we would estimate this at 2,400 javelinas. Okay? Now this type of estimation process is something you may also be asked to do on the CLEP. To estimate some sort of number that you can't quite compute exactly. So the trick here was to do 2 to the 9 halves. I said, well, that must be between 2 to the 4th and 2 to the 5th. Because 2 to the 4th is less than 2 to the 9 halves, and 2 to the 5th is greater than 2 to the 9 halves. I can compute 2 to the 4th, it's 16. I can compute 2 to the 5th, it's 32. So of course, the quantity I'm interested in must be between them. And I estimated it as being the average of them, right smack in between. That might not be reasonable in general. In fact, I'm pretty sure 2 to the 9 halves is closer to 32 than it is to 16. But for this type of thing, usually if they ask you to estimate, you won't have to do too much clever stuff. Just the straightforward estimation. So now let's look at the hardest question here, which is asking us to do something a bit different. In B, we were asked how many javelinas we had after a given time. Part C, I want to know how long until I have a certain number of javelinas. So I want to know how much time must pass until I have 1,000 of them. So I want to know how long until the population of javelinas equals 1,000. So how could I do this? Well, this winds up just being an exponential equation I have to solve because P of t is given by an exponential function. So before I plugged in t and computed P of t. That was easy. Now I want to solve for t here. So I'm given a certain exponential function equals a constant. And I want to solve the exponential equation. So I'll write 1,000 equals 100 times 2 to the t divided by 16. And I have to solve for t here. So how can I do that? Well, let's first divide both sides by 100. And we'll get that 10 is equal to 2 to the t divided by 16. And now I want to figure out how to get rid of this 2 in the of the exponent. How can I do that? Well, what function kills off exponential functions? The logarithm. So I'll take a log base 2 of both sides. So log base 2 of 10 equals log base 2 of 2 to the t divided by 16. That logarithm kills off the power to the of 2, and I just get t over 16. So I have t over 16 equals log base 2 of 10, and then I solve by multiplying both sides by 16. So we get t equals 16 times log base 2 of 10. And again, you might be asked to do some sort of estimation. Log base 2 of 10, well, that's between 3 and 4, because log base 2 of 8 is 3, log base 2 of 16 is 4. But in this case, it would be closer to 3. But I won't ask you to do that type of estimation here. So let's just review how we solved this last exponential modeling problem. I wanted to know how long until a certain quantity was achieved. So to do that, I set my model equal to a number and then solved for the variable in the model. This required me to use a logarithm. And this is very typical for exponential models. Well, you'll at some point be required to use a logarithm. If you're feeling confused or you're feeling a little bit uncomfortable with logarithms, I recommend two things. Go back and watch the videos we already have seen about logarithms and refresh your memory of how this is a very powerful tool for exponential equations. Also, take a look at the reading and the exercises I have suggested for this topic, which will show you additional detailed examples of how to solve these types of problems.